Hello, my name is Jamie. So I've been muddling about where to start with introducing Cadquery and its API. There's a lot going on, and I think it's important to just get something on the screen so you can see it. I wrote up documentation, specifically one-liners that show off aspects of the library. And so let's talk about that and how it's organized. So this is a gist. It's up on GitHub. I'll link it in the description. And the way it's broken up is there's a breakdown of 3D shapes, sketch shapes, and 2D shapes. And then at the bottom are common operations. I suspect this document will get organized differently in the future, probably shifted around, but I don't plan on breaking it up. Um, because one of the features of having it all in kind of one place like this is effectively doing Control F and doing search against this is very straightforward. So once you get more familiar with the library and you go, okay, well, how do I build a box, or how do I do a cone, or how do I do a loft or a chamfer, or how do I do a twist extrude? You have basic one-line examples showing the feature off. When you get into Cadquery documentation proper, this guy, what I found is that while this is good, this is excellent documentation, the tricky bit is the output is very visual, right? So I want to be able to see along with like examples very quickly, small examples specifically. I want to be able to see what the output is just from yeah, it's a very visual aspect to it, right? So we're talking code, but there's a very visual aspect out of it. So if we go to like, where is it? Not the cheat sheet. Let me just kind of skip through this a bit. I'll show you what I'm talking about. 2D operations. So this documentation is not bad. Let's go to the next bit. Yeah, we get into principles, and we'll talk about this stuff in the next video. But this is where it gets heavy for me. So when we start talking about like 2D operations, and it'll kick you out. Here's all the 2D operations. There's a visual aspect that I want to see to this because I can probably quickly more align to what I'm looking for if I can see some output of each of these kind of things kind of individually. And the same for 3D operations. Like this is really good and I get a rough gist of what it's doing, but I don't know the exacts. So instead of belaboring about that, let's just start talking about it. So with each of these examples, you have a screenshot, basically a header, the link to the documentation, the one line bit of code you need to actually run it, and then a screenshot of the output. So for example, with Box, let me close these other tabs. Here's the documentation for Box, sorry. Its various parameters, and then here's a one-line code in order to get um, Box off on the screen. And I already have it, so basically you can run it. Show object is actually kind of optional here because it's just going to show what's ever on the stack. And then we can start changing the parameters, right? And let's just make this 10. And so there's not a lot for me to extrapolate off of this that I want to do right now. Part of this is just highlighting that this documentation's out there. I wrote it up, and you can use it as a resource. Here's an example of making a cone, a cylinder. You see, I'm kind of shooting through these quick. A sphere. One thing I will note is like when you get into some of these, they'll have multiple ways of doing the same thing. And effectively, Cadquery is built off of 3 layers of APIs. And I won't go into the specifics of that right now, but where possible, if you can, try to use the work plane version of the API call. And these ones in later versions of Cadquery may not be as exposed. Because effectively this is a lower tier, a more primitive version. I don't want to say primitive. It's a different layer of the API, and really what you want to be calling is the ones at the Fluent API level. Prefer that. All right. So here is doing text. You can actually do a lot with the text. There might be some more notes I want to make for cone, but that's okay. So for text, you can define what the test string is, which is actually pretty cool. And you can also, when you get into the parameters of these things, you can define out what the font is. So what the font path is, and potentially, and I'm guessing that's on the operating system level, what the font name is. Here's making a torus. This is again in the solid library. There isn't an option for it in the Fluent API level yet, although I think it is on the roadmap to also get that moved up to the Fluent API. Wedges are funky. I'm not going to delve into everything that a wedge has because I have a very bare bones understanding of what all the attributes mean. Effectively, you can you can cut off the top and you can change the alignment of the wedge. So it has, yeah, these get very abstract to me very quickly for what these values represent. All right. Then we get into, so that's the breakdown of 3D shape primitives, how to just get stuff on the screen, and basically one-liners to achieve it. And then you can modify it, look at the documentation to get into explicits about these things. Um, the sketch shapes is going to be probably a whole other video in its own right, but sketches are effectively a way to make a face, a 2D face, and then either extrude it or apply it. So it's basically setting up a series of 2D operations, finalizing it, and then getting a face output from it, as opposed to further down where we have just the 2D shape operations that generate off wires. So we have various arcs, and there's one thing to know is that right now this documentation isn't exhaustive. It's a lot of kind of common examples, but doesn't cover every operation available in Sketch or every operation available throughout the API, right? Um, so to make a circle, this is what you need, an ellipse, and I'm kind of rushing through this, but it's more useful to see it in practice, right? Um, Polygon is kind of cute. So what that is effectively you're setting up, um, let's output that, assuming it works. And sketches are a little bit funky in that regard, so you did need the show object. It's the main point with the sketches you saw is it didn't go immediately on the stack. It's when you finalize it and add it to a work plane is when it would go on the stack. So with a polygon, let's show the documentation for it real quick. Basically, you pass in a radius and you pass in the number of points. And so if I give this a radius of 5, this means it'll be a diameter of 10. Not that that changes much, and we'll say the number of points. When doing this is regular polygons, so these are the length of the faces and the number of points. The length is always the same, and the angle is always the same. Um, and let's change that to say 7. And so what it's doing is it's basically drawing out a circle. That's why it's taking a radius. And then it's using trig in order to determine from the center point where each of the points would land that would be equidistant. So let's change this. And you can see it like, so if we make it 100, you can see that it's very, that's why it's a circle, right? I'll do 10. And so the more points you have, the closer it gets to a circle. Um, there we go. Okay. So back to the documentation. Um, built-in slots. Splines are good for doing sweep operations and various extrudes, complicated extrudes. All right. Trapezoid, this one is funky. This one's unique to Sketch. It doesn't actually exist in the 2D shapes ones, which is interesting. So now we get into 2D shapes, and here's the listing. I should probably add that for the other ones. Yeah, so here's the overall list of operations, 2D operations, and you see there's a number of them. Kind of clean up what I'm dealing with here. And then here's the actual generate out of this. So what these are doing is they're making a wire which you can then perform operations on in order to make them either a face or to make them a higher order of magnitude objects, right? Um, Drawing an ellipse, drawing a helix. This one is particular in the examples that they use is for doing a sweep across. So picture having like a circle down here and then sweeping it all the way across the helix. Um, Various line segments. There's line two, and those have different implications in usage. There's a crap ton of arcs that aren't in this documentation yet. Drawing a rectangle, drawing a polygon, similar to the sketch one, except it's not a face here, it's just the wire. And the advantage of having just the wire out here is so this can be made just as a construction based object. So generate off the polygon. I can show you. We're going to copy this, go over here, paste it, and here's your polygon shape. So with this, we can change it so that it's for construction. And I always forget the exact name of the parameter. So let's go to for construction. So here's the documentation. Here's the key I'm looking for. So if we mark this as for construction, bam, and say equals to true, won't change much on the output here, but what we can say is now we can select attributes of that. And in the final output, this wire set will basically be removed out from the stack. It won't be in the final render. So let's say we'll select off the vertices and highlight that. So that highlighted just the vertices. And then we'll say add a box at each vertice. And I got myself in trouble originally when I was doing this demo because I tried to do another wire off of it. And I think there's some other operations I need to do in between, which I'm not going to cover right now. Basically to set it to like to pending and to basically get multiple of those going. So we're just going to say a box. And I'm going to say one and one and one. And so what the hope is so we have a polygon with 6 points and for construction is true. And then at each of the vertices, we're going to set this one and one. And let's see if that does anything. And okay. And I wonder if that's where I'm messing up. So let's say 3. There we go. That's where I'm messing up. Okay, I gotcha. So let's show what we have right now. So somewhere in here, I messed up that code. Okay, and expand that out. So, oh, yeah, that would do it. Okay, so let's set it up to 10. There we go. So that's more readable. And then we have 1, 2, 3, 4, 5, 6 vertices, and we'll change it from here to say 10, and we'll set it to 3. And so that's where that for construction bit comes in. If we don't set for construction, you'll see it in the output. Well, I think you would. Okay, I'm not going to belabor that right now. And instead of saying vertices, let's do faces. And what did that do? Nothing good. Okay, I'll roll with, what about edges? Oh, because there's only one face. Oh, gosh darn it. That's why I was getting messed up. Because it's a wire, there are no faces to it, or there's one. There we go. So that's better. So let's change that to 6. Yeah, okay. So originally when I tried to show this demo, I messed it up thoroughly by trying to say faces here when I really meant vertices and edges. Okay. And so if we show the original shape, here's the polygon that we defined out. And so let me double check. What are we doing? We're saying how many sides it has and what the diameter is of the polygon. So not the radius, but what the diameter is. And so we're basically saying it's got to have 6 sides, 6 points, 10 diameter. We're going to say it's for construction true. And then on the edges, we're going to set up boxes, right? So on each of these edges, in the center of that, we're going to add a box. Or we can say on the vertices, which is the points, we're going to add a box. Bam. And additionally, is there any additional thing I want to add to that? You can do selectors. So if I say X, what this should do is about half of the vertices will disappear, I think. We'll see. Nope. Um, only one of them showed up. If I say X or let's say perpendicular to X. No, that didn't work either. Um, do I want to fight with that right now? There's something I'm missing. So what if I say Y? So that's in the positive Y. And what if I say or X? Nope. Okay. I'm not going to fight with selectors right now. So that's good enough for the moment. So the gist is you can write out wires, you can use them as a construction element, select out aspects of it. In another video, we'll cover selectors, and I'll actually get my demos working, and then we'll have the showing adding additional elements at those points. Uh, and when you go looking at this documentation, where is it? The concepts. Next one down. Is that it? No. Here, this. So all of these are selectable elements. So the vertexes or vertices, the edges, the wires, the faces, those are all selectable elements, subcomponents of a shape that you can filter out when applying iterative operations. All right. Meanwhile, so Polyline, which I kind of skipped over with the sketch side, is effectively setting up a series of points. So this is an array of tuples, and this one's worth talking about because this is allowing you to make custom custom outputs. Basically, you're setting up a series of line segments, right? So here is the shape or the wire. We can apply. Oh, and that might have been yeah, part of my hang up too with the previous demo. So we set up a series of points. We can customize the points somewhere in the middle of this guy. This guy. So we're saying 2, 3. What if we say 6 along the y-axis? There we go. And so you can customize off your points, add more points, make pretty much whatever 2D shape you want to make, and then at the final, if you want to make it a 3D shape, you can, extrude it. So extrude 4. There we go. All right. So we have polyline, slot 2D, similar to the slot 2D in Sketch. Spline is a line segment or a series of points that forms, instead of a hard angles, like this guy, it'll basically draw an arc in between the points, effectively. Then we get into operations. So extrude, we just showed off a little bit, working off of a polyline. You can also do it with any of the wire shapes, so the 2D primitives, the rect, the circle, pretty much any of the wires, as long as it forms a closed shape. Um, Here's a fillet operation, and that one's kind of worth looking at. You can get yourself into a little bit of trouble with fillet because it is going back to the Open Cascade library. If you get into errors with it, it gets very abstract. So let's put in this guy. So here we're drawing off, we're selecting the work plane, X and Y. We're drawing out a box. We're selecting the edges on the box. And this is actually a good use case for showing off selectors that might actually work. So if I say I want to grab the edges that are perpendicular to X, there we go. And that actually works. Or if I want to grab the ones that are perpendicular to, well, let's say, or I want to grab the ones that are on the z-axis. There we go. Um, okay, more to cover with edges. So this is a selector operation. So we have a box. We're going to select the given edges on this guy, and then we're going to do a fillet operation. And I suppose this doesn't have to be just on the edges. You could just say it's on the vertices. And what will that do? Probably break. Okay, it wants edges to be selected. So fillet wants to work with edges. Fair enough. I won't fight with it. And where you can get yourself in trouble, what I was alluding to, is if you set the fillet too high, this code will have a fit. So if I set it to, say, 4, it should start getting rounder and rounder. If I set it to 5, might be the breaking point. Yes. All right. So that's about half of uh, the box. It is basically a form of sphere, and it starts getting a little grumpy about that. So if I say 4.9, that's just shy of being a complete sphere. And so it's okay with that. If I say 4.999, that'll be fine. Now it pretty much is a sphere as far as like rounding and flooring the math goes. As soon as I skip over into that 5 threshold, this code's going to stop working. So that's one thing to know when working with fillet is you want to be a little bit careful about pushing too high. And if you're dealing with small scales, so if your box isn't very big, so let's say 2 and 2 and 2, so 2 millimeters by 2 millimeters by 2 millimeters. When you get into this guy, so anything above 1 will fail. But if I go lower than 1, so say 0.5, that'll work. So you want to be careful of your scaling, when working with the fillet operation. Um, and chamfer is not much different. So this section that we're really talking about is the operation section. So these are either working on 2D or 3D shapes. So some of them are dependent upon one versus the other. And that's where I can do a little bit better with organizing this documentation. But anyways, operations are you have a shape or a 2D primitive, and you want to apply an operation to it. So like fillet, extrude, chamfer, and chamfer follows a lot of the same shenanigans that fillet had as far as the applying it with the scaling, right? So here we're making a work plane, a polygon, which has 6 sides and a diameter of 20. We're going to extrude it out 10. We're going to move it off of we're going to center it. So this is doing a translate. So we're going to move it. This is the X translation, the Y translation, and then the Z translation. So we're taking the height of the extrude, moving it, dividing it by half, and then timesing it by -1 in order to turn it into the negative. So we're going to move it down -5 millimeters. And then once we get our shape off of that, result is not defined. You're correct. Once we get our shape off of that centered, then we're going to apply a chamfer operation. The interesting bit is it didn't complain about having the edges defined. So I'm assuming it's just going to default to all of the edges off of the chamfer. And that's cool. So let's show result. What does that do? That's better. All right. So if I say dot edges, that should be the same effect. And if I start selecting out the edges, let's say the ones that are on Z, and yes, that did work. And let's say or uh, uh, positive X, yeah. And let's say that's cool. And let's say or negative X. There we go. And what am I doing with this thing? So I'm saying chamfer the edges, which is kind of like fillet, but you set two values to it as opposed to one. And so like the chamfer is effectively like the height and the travel distance. So if we set this to 2 and 2, so now it's steeper. So the first one basically sets how steep the chamfer is, and then the second value sets how the kind of the on the X and Y plane, how long the length of the chamfer. There we go. And so with these selectors, what I'm saying is grab the ones, all of the edges along the Z axis. Okay, great. We'll do the cut operation there. Grab all of the edges along the positive x-axis, and then grab all of the ones along the negative x-axis. And so by default, when you just say x, that equates out to positive x. And what that means is at the origin point, the 0, 0, 0 origin point, uh, grab the edges that are in the positives for the x's. So if I take this off, every edge that's at a negative below before the at negative x should be excluded. And yes, that happened. So right here, this edge counted as being positive x, whereas this one counted as being negative x. It's on the negative side. And the similar way we could do this is we can say pipe and y, and this is saying grab the edges that are perpendicular to the y. And did that do anything? Did not what I was hoping for. So I'm going to ignore it. All right. Uh, and we'll just apply uh, that guy. There we go. All right. So we talked about chamfer. We get into hole. This is a cut operation. I think honestly, I would treat this more as like a plugin, but effectively this is drawing a circle and then cutting through the shape in order to place a hole in your object. And we can show that real quick. Bam. And let's see. Okay, so here we have our hole, and this is setting basically the diameter and the depth. So if I do 3, what does that do? That's a good question. How about, oh, that's probably the depth. Nah, I'm not gonna worry about that. 2. Yeah, okay. So that's setting the diameter. What is the second value setting? So the diameter and the depth. In this case, it's a very small object, so the depth doesn't make a whole lot of difference because it's only 2 by 2 by 1 height. So what if we do 0.5 depth? There we go. Okay, cool. All right, so that covers, we talked about hole. Then we get into loft. Loft is funky in that you're basically taking two wire planes, two primitive wires, and then drawing faces between the two of them. So let's grab that. So it works. So the gist is we grab our work plane, and let's separate this out a bit. We grab our work plane. We're going to draw a circle with a radius of 1.5 millimeters. We're going to grab a work plane off of this, off of the circle. Let's comment that. Was never closed. Yeah, you're right. And will it show it? No, because I grabbed the work plane. So show the circle. All right, so we grab a circle. We grab a work plane. We're going to offset the z-axis up by 3 millimeters. So we're going to grab a relative work plane, offset the z-axis by 3 millimeters. We're going to draw another rectangle. And I shouldn't have to do any of that. And so we had circle, but in the working stack right now, so we have a circle, we have the rectangle, and then between the two of them, we're going to do a loft and say combine the non-extruded wires. So basically all the pending wires, we're going to combine them. And we get something like this. And so we can change the shape of these pretty freely. You know, instead of doing a rect, we could do a polygon. I don't know how this is going to work for the sake of the demo because I haven't tried it. And we should be able to say the number of sides will be, say, 5, and then the diameter probably shouldn't be much bigger than the circle, or should be way bigger. We're doing 1.5. Let's try like 1.8 or 0.8. See what that does. There we go. Yeah, so that's a loft, and basically it's trying to basically draw faces to match up with the other wire. So between the circle and between the polygon is trying to connect everything. And that's cool. Okay. So then we get into rotate. Rotates are just strictly translating it. Okay, so there is some stuff to talk about with rotate. Um, rotate has basically a tuple saying along which axes to perform the rotation, right? So we have X, Y, and Z. So in this case, it's saying perform the rotation on the Z axis. And it's easier for me to just show it in the editor. So we're going to draw out an X. And we're not dealing with results right now, we're doing rect. So we draw this guy out. I'm going to turn off rotation. Here we go. And so when we apply rotate, we're applying basically this Boolean tuple. So along each of the axes, how should I perform the rotation? You can do multiple axes. So in this case, that's the Z and the Y axis. It's doing the rotation. And so the first tuple is begin rotation. The second rotation is end rotation. And we can see that in the document. Yeah, so axis start point, axis end points. This one I'm not uh, entirely familiar with. Basically, you get off like more diagonal rotations when you start playing with the second tuple. And it gets a little bit odder. And so I tend to focus on the begin rotations for most of what I'm doing. There's circumstances, I'm sure, where you need the end rotation. And then this other value, the third value, is the rotation degrees. So if I set this to 45, um, boom, 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 not 450, although that could be fun too. This should now match up on the axes. There we go. And so you can set it in the positives, you can set it in the negatives. So we'll go back to 30, but set it to negative 30. And there you go. So that's basic rotations. Boom. Sweep operations. Okay. So effectively, in this example, let's talk about what we've got going for a sweep. So remember we were talking about the helix, and if you forgot about that, this guy. You could basically lay down a shape primitive on your axes, draw off a line, and then sweep would rotate it around. And so this is a very simple example of doing that. So let's show some stuff. We have defined out points. That's going to be placed against the spine, spline, not spine. And if I show that, there is our spline, right? Then we have a rectangle, basically a 2D path of a rectangle. There's our rectangle. We can show both the spline and the rectangle. Boom, there's together. So when we apply a sweep, we're basically going to say grab this rectangle and drag it along our curve. And so what that'll do is it'll fill in, these are basically our keyframes. So here's our travel path, and here's our starting shape. And so finally, let's show results. And we'll say rectangle, sweep, bump, bump, bump. And so I can show them side by side. I'm going to say translate. I'm just going to offset it by like 10 and 10. And that should be a tuple. And watch as this code breaks. Yeah, no pending wires. Result. That's because I don't need that here. I need that here. I thought I was being tricky. And let's do show object result. Will that work? Yes. Okay. And I don't need it as aggressively pushed off. Let's say like that. And 5. There we go. That's not too bad. And so what it did was it drew, yeah, that's a very good example. So we're showing our path, which is the spline curve. We're showing the origin shape, which in this case is this rectangle that we're drawing out on this line, and then show the sweep. What's doing is it's basically dragging the rectangle along that path, and that's the finalized shape you get out. Um, Going with, if it's not broke, don't fix it. Um, let's swap this to a polygon just to show that I'm being honest with you. So 3 and 3, that should be a triangle with a diameter of 3. Works for me. And now we've done a sweep operation. So any shape primitive, you can do a sweep across and get some very complex geometry out of it. And then, the spline, you can add n number of points to it, right? So I don't know if this will work, and I'll probably break some stuff. But what if we did 3 out and so what would that be? That's along the x-axis, so we're going to go out to 3, and then along the y, what would that do? I don't know. Let's try it. Probably break it. There we go. Yeah. So you can set up your travel distance however you want, and there's all kinds of different sweeps. It doesn't have to be a curved distance. It could just be a straight line extrude, or it could be a diagonal extrude for that matter, right? There's a lot of neat things you can do with sweep that, yeah, it's cool stuff. Okay, so let me go back down to operations and sweep, and I gotta find it again. Okay, then we have translate. We actually just talked about translate by pushing it along the X and Y axis here. So that talks about translate. It actually takes, you can put in a third value, and that would be along the Z axis. So that'll push it up 10, which is kind of aggressive for this demo, but that's okay. Okay, and then we get into twist extrude. Okay, this is taking a 2D primitive and then extruding it, but applying a twist to it. Yeah. And effectively, twist extrude is the height that you want to go, and then the number of degrees for the extrude. So let's change that to 3, and we'll change it to 90. Boom. So that did that full rotation. And it doesn't have to be a rectangle. Again, it can be applied to whatever you want. That, and just for giggles, let's go grab this. So in this case, we have a different shape. It's got an inset to it, cut in it, and polyline. So I'm going to change out my polygon for my polyline. I am going to say dot close. And so what I should get is based off of these points, I'm going to draw a 2D polyline that looks like this. And then we're going to twist extrude it off 3 millimeters with a twist of 90 degrees. And that gets very strange. Cool. Oh, so what if I did, let's say 5, and we'll do 180. It's cool doing it with, oh, and because it's not centered. Oh, so that's interesting to know. So the twist extrude worked off of the center point of the origin point of the z-axis. So when it was twisting it, it twisted it along that. So let's say 180. That's an aspect I missed. Cool. Yeah, so it's rotating along that. So if we did a translate beforehand and say we brought it in um, -1, what is this? Let's just try -1 and -1. This this should start looking more like a column and get less aggressive in this full rotation. So let's try it. And my translate didn't take. Yeah, yeah, yeah. It was never closed because of the tubal. Yeah, so if I bring this in at 2 and 2, okay, so now it's roughly centered. Now when I do the extrude, it should be extruded along that, right? No, it's still offset. Okay, so there's some more work I got to do there to understand what's going on. What I could do, okay, so let's ignore the translate. If I do move the center point to -2 and -2, and this one isn't taking a tuple. So if I say move the center point, draw the line out, and then ignore the extrude, should have the same net effect there. Okay. And then, so now if I do the extrude, a little bit better. It moved it, that's for sure. Okay. Stuff to play with. All right. So that talks about twist extrude. Neat stuff. Now we get into the next section, the final section, and this video is dragging on long enough, is we have plugins. So there's a plugin for a cboreHole, which is basically cutting out a metric screw. And then there's also a countersink hole. And these are both very similar to each other. So effectively, let's look at cboreHole. Show that one. So we're grabbing our work plane along the X and Y axis. We're drawing out a box. We're selecting the face that's on the positive, so the most furthest out, the greatest face along the Z axis. And then we're going to do the cboreHole. And this is, I think, inner diameter, outer diameter, and then depth, I believe. And because the shape is fairly small, inner depth. So inner diameter, we'll say 2.5. Yeah, should expand that. And then outer diameter, we'll go a little bit higher. We'll say 6. Yep. And then the inner diameter will shrink up. No, the cut. Oh, I keep messing that up. Let's say 3. There we go. And so that's for defining, like, here's a screw path and here's the head when you want to sit in. And typically the metric screws will have this kind of shape. And then the CSK one, so we have cboreHole If we say CSK, that's for the countersink screws. So the stuff that have, and I'm drawing it out with my hands, but you can't see my hands. The stuff that have more of a curve. And let me just grab the example for CSK because my values are probably too extreme right now. Bam. So the stuff that have a more gradual um, gradient. Okay. So there is the documentation, and we talked about it. So next videos, this just talks about uh, simple operations with shapes with examples. Next ones are going into concepts of CAD query, as in work planes, uh, selectors, sketches, assemblies, um, and we start talking about kind of workflow more or less.